Okay, thank you. So let me first introduce myself. My name is Brad Beck from Los Alamos National Laboratory, and I have the honor of introducing all the speakers this morning. So our first speaker is Paul Miller, who I've known for about 15, 20 years, so it's kind of nice to be able to introduce some of your colleagues. Paul is the Associate Director of the Design Physics Division at Lawrence Livermore National Laboratory. He heads an emerging projects and collaboration efforts focused upon new mission projects and interactions. And that's exactly what we're going to see today as a talk, which he is one of the ones who hasn't changed his title from the program, as I noticed, which goes into the NNSA activities in planetary defense. Paul, through experience, has been helping out with the SSGF for years, and has been key in a lot of these selections of all of you out there. So I wanted to make sure he knows that, everyone knows that. This project that you're going to see is NNSA. It's actually the whole laboratory. So he's representing a lot of work done at Livermore, but also work that's being done at Sandia and at Los Alamos. So with that, I hope you welcome Paul, and I'm sure it'll be an exciting talk. So welcome, Paul.
Thank you, Brad, and thank you for the promotion. I'm actually an associate division leader, but I appreciate the thought. So as Brad said, I'm giving an NNSA-wide talk. It's actually a four-site talk. Both Sandia Livermore and Sandia Albuquerque are involved, people from Los Alamos and people from Livermore. And so I serve as the technical lead for the NNSA effort. Dr. Kevin Greenow at headquarters is the federal contact for the effort. And it sits within Dr. Kathy Alexander's area. You may have met her last night when she came. So I'm going to talk about the asteroid impact hazard and our activities in support of U.S. government understanding and potential response should an event develop. And so I'll go through some background. I'll talk about how the government's interested in this, touch upon why the labs are involved, and then I'll get into really the key issues, which are what can we do about this, including emergency response, deflection of the objects to prevent the impact, or even disruption and spreading and deflection of the objects. And then I want to talk a little bit about the research drivers. What makes this a scientific and technological challenge, and where are the problems to be solved? But the asteroid impacts are a national security threat requiring advanced science and technology solutions. So I think that summarizes why the NNSA science labs are involved in this. National security, science, and technology needed to provide solutions and understanding of the problem. So there are thousands of near-Earth asteroids, and they continue to be discovered. NASA has a very robust and active survey program of ground-based telescopes that is looking for near-Earth asteroids. Now, these are not the typical main belt asteroids that lie between the orbits of Mars and Jupiter. These are asteroids that come closer to the Earth's orbit, across the Earth's orbit. So this is a depiction of a variety of orbits of some of the objects that are known, and the red circle depicts the Earth's orbit. The outer circle is Jupiter, and there's a faint white one that's about here. And so you see that these orbits have a lot of ellipticity, and they're basically coming in. They probably were born out in the main belt, but something happened, a collision or a perturbation that pushed them into a resonance area, and they start visiting the inner solar system. The graph on the left depicts some discovery rates over 6-month intervals, and the different colors are some of the different facilities, the capabilities of detecting them over time. But the main point here is there's two terms. We often say near-Earth object. It has a specific definition that its closest approach to the sun is less than 1.3 the average distance of the Earth from the sun. There's something like 11,000 of those that have been discovered. and close to 1,000 of them that are 1 kilometer diameter or greater. Now, of particular interest actually are even more hazardous asteroids, termed potentially hazardous asteroids. The definition for those is that they come within a 20th of an AU of Earth's orbit, and they have an absolute magnitude greater than 22. The reason for that is absolute magnitude or brightness is being used as a proxy for size. And they have different brightnesses, but that's what's observed, and so it's easiest to define them. So the bright ones must be, relatively speaking, bigger and are more hazardous, more concern. So the impact that most people today are familiar with was the Chelyabinsk event that occurred local time, 15th of February in 2013. This was a roughly 17-meter object. It approached from the east over the area in the morning, and it was a chondrite object, a common asteroid material. It's a lot like Earth rock. You can see a piece in the middle there. And the object did not survive to the ground. When it was entering the atmosphere, it basically had an energetic event and broke up in the region of the maximum dynamic pressure as it was entering the atmosphere and coming down into the denser air. And it basically exploded at altitude. When its maximum brightness as it was coming in was briefly brighter than the sun. Shadows from videos were used in order to calculate the trajectory of the object. There's a long story I could have about this, but in the end it broke a lot of windows, collapsed a couple of walls and roofs, and injured something like 1,500 people, almost all from broken glass injuries. Now, before Chelyabinsk, probably the two most famous impact events bracket the range of interest. One was the KT impactor in the Yucatan Peninsula of Mexico about 65 million years ago, and that's associated with a mass extinction event. The other was the Tunguska impact in northern Russia in Siberia in 1908. There were no local observers, but the effects were observed from a distance, and investigators, when they arrived, they found a forest that had been leveled over an area approximately the size of the Washington, D.C. Beltway. That object is estimated to have been about a 30-meter to 40-meter diameter object, and it knocked down a whole forest. And so this graph shows an approximation of the circles and then of the estimated population of near-Earth objects. The dashed line is a power law approximation. And the scale here is 10 kilometers, 1 kilometer, 100 meters, 10 meters. The point is that the small ones are much more numerous and therefore much more frequent as impactors. The large ones, much less numerous, much less frequent, but that the damage is increasing with size, particularly since really mass is important, and so it's going like the cube of the radius. And something in the multiple hundreds of meters diameter to kilometer scale is generally considered to be of size sufficient to create global catastrophes. It's where you're really getting concerned about global effects. Sizes from 100 meters to 500, 600, 800 meters. You get strong regional effects depending on the scenario. Below 100 meters, like you can see with the Tunguska event and even Chelyabinsk, you'll get localized events. Depending on where it hits, it could be really bad. So the U.S. government's been aware of this threat for quite a while and has expressed its interest over decades. Starting in 1992, Congress tasked NASA with what's sometimes called the Space Guard project of locating the objects greater than a kilometer in scale. But that evolved over time with additional mandates through congressional legislation, and there was some back and forth between the administration and Congress back in 2010, OSTP and Congress, and they basically were saying, okay, we need to form up some sort of effort on this. NASA, you have the lead, is what the administration said, for dealing with this threat. And about the same time, sorry, wrong button. About the same time, the National Academies, National Research Council, produced a report called Defending Planet Earth, which gave an overview of some of the issues. Since then, FEMA has become involved, and there have been 2 exercises in 2013 and 2014 in which we participated. NASA organized them, and this was looking at the consequence aspect of a potential impact. FEMA wanted to educate themselves about this threat that they were underinformed of, and in the course of that, they've learned a lot about it, and they've added it to their list of bad things that can happen. And they have a very interesting perspective. They're looking for similarities and differences. They say, oh, if it's coming for a city, you have to evacuate the city. We got that, we know that. Okay, what's this about this blast damage? What about this shock wave? We don't quite understand that. That's a little new for us. Okay, so there's been a lot of activity in the background there. So why are the labs working on this? Well, it turns out there's a lot of connections to expertise at the labs. Now, the one that people usually presume, and that the media presumes in all the articles you see, is that, well, NSA's involved because we're going to use a nuclear device on these things. You got to go get the guys with the nukes and get them involved. Yeah, okay, so if you're going to use, we got a guy, right? But you know, it's more than that. It's the stuff that you're aware of and that other people that collaborate with us are aware of. It's about our multiphysics modeling. It's about our high-performance computing. It's the unique algorithms that we've developed. It's our understanding of equations of state and opacities. And all of this, as I'll show a little bit later, come into the problem. They're central to the problem. And we're class leading in these areas as well. It's not just our monopoly on nuclear weapon design and understanding the physics from those detonations. It's all of this other stuff as well. Uncertainty quantification, material strength, hydrodynamics. It turns out, and this was, I wish I had recognized this ahead of time, it would have looked brilliant, but we've got into this topic, and it turns out it's a microcosm of the weapons program. Except for radioactivity and radchem, apologies, Kim, I don't know if you're back there, it's got just about everything, including potentially a device that's going off, if that happens to be the scenario that one wants to examine. So our primary goal is to support the U.S. government agencies in their needs. They have needs, and NNSA can deliver those needs uniquely. Okay, so that's our primary goal. And as part of that, we need to assess, well, what are the U.S. capabilities? How effective would they be, whether they're nuclear or non-nuclear? And also, again, because we have the expertise, we're involved with the assessment of impact effects on Earth. So terrestrial, water impacts, air bursts. So we're working with NASA. We have an interagency agreement that was just signed late in the spring. We're working with NASA headquarters and the NEO program office, which is actually located out at JPL. We're engaged in the premier conference that covers this topic. It's called Planetary Defense Conference. It's held every 2 years. We worked with other agencies such as FEMA and DARPA, and we have collaborations with all of the key NASA sites that are involved in the problem right now. And while we're doing this, it provides additional benefits as a side benefit. It strengthens related expertise. It stresses us if we use algorithms and methods in ways that are new and outside of our usual application, it can reveal weaknesses. It can illuminate their behavior. And so we find it very challenging to take things to new regimes. And it also provides a natural engagement with the community. There's a wide academic community that's planetary science community, engineering community that is interested and engaged in this. We've had 2 postdocs. The first one, this started as an LDRD at Livermore on our side about 3.5 years ago, almost 4 years ago now. And Kirsten Howley was the first postdoc, and she was the center of the project, and now she's employed in our division at Livermore. The second postdoc, Megan Brooks Sayal, came from Brown. She's a bona fide planetary scientist, but she's doing the simulations and the modeling of the impact. You'll see a few examples of that. And we've had a number of summer students. We've had 4 or 5 different summer students involved with this just at Livermore. So what can we do about an impending impact? First option is you take the hit. There's nothing you can do about it, or you decide not to do anything about it. Maybe it's small enough that you say, this is not worth a huge effort, spending billions of dollars to try to stop this. It's little. You figure out where it's going to go. Maybe it's just going to drop in over the ocean or a desert somewhere. You just get people out of the way. Well, you need to know what's going to happen if you're going to do that. And so this is an example of a water impact assessment done by Suhail Ezzedine at Livermore. And he starts with modeling the impact into the water with the ocean bottom underneath and developing that as a source term. And then he couples that source term into a wave propagation code and propagates the wave. So on the right, you see an example from the FEMA exercise in 2014 of a potential impact in the Gulf of Mexico and the resulting wave pattern several hours later. And this is the kind of thing that FEMA wants. They want to know, in Galveston, how high will the wave be? When will it show up, and how high will it be? And so for this particular scenario, these were a few meters in height. This was 3-meter waves on the coast in some places, which in the Gulf, especially if combined with a high tide, would be a bad day. It's like a hurricane storm surge. And so this was work done in conjunction with Sandia NESAC Center, and they used some of their mapping capabilities to take our simulations, drop them in, and you know, if you were looking at this, you could see the various wave heights and arrival times on the graphic. So this is the kind of information, same thing for terrestrial impacts, same thing for air bursts like Chelyabinsk. The government wants estimates of what's going to happen. They need somebody to tell them either this is going to be okay or this is bad. How bad is it going to be? What things are going to happen? But we'd rather prevent this, or if it's going to be really, really bad, right, we don't want to see this happen. Now, these things are not very likely. We're talking about, there's still some discussion in the community about the frequency of these events, but Tunguska, a Chelyabinsk to Tunguska size event is probably multi-century, but not too many. Could be 100 years for Chelyabinsk, could be 300 years for Tunguska, kind of on that ballpark. Bigger ones, the frequency drops off. The KT impactor frequency, it's hundreds of millions, it's 100 million years, 50 million years kind of frequency. It's not very likely. So the idea is you get the surveys to find these things ahead of time. You determine whether they're going to hit the Earth. So far, they have not confirmed anything's going to strike the Earth. That's on the current list, although not all the probabilities are zero because there's uncertainties associated with the measurement. And when you propagate the uncertainties, you end up with residual probabilities of impact. So you can go to the NASA JPL NearEarth Object webpage, and they have the list of all the objects that have non-zero probabilities currently. You can look at the list. If you integrate the entire list, you come up with something that's about 3 or 4%, I believe, right now, but that's because there's one small rock that has most of that probability associated with it. If you remove that, I believe it's below 0.1%. Okay, so one thing you could do is you could deflect it, like checking a hockey player. Well, I don't have to explain to the scientific crowd. I'm getting used to talking to the public. But basically, it's momentum transfer. You use some momentum, or you generate some momentum with a device and blasting off material, and then you affect the timing and the direction of the orbit. So one way you can do this is you take a lump of mass and you slam it into the object. So it's referred to as the kinetic impactor approach, and so this is a calculation by Mike Owen at Livermore using SPH type of code of a kinetic impact. And you see colors representing velocity of the material coming off. The bubbly nature, that's very low density stuff, and it's a graphical conundrum with SPH codes of how to display that. But you have this material that's coming off, and it also shows the damage modeled of the object. So this is a code that can calculate damage, cratering, and ejecta. And so what happens is, not only do you get the momentum imparted of the mass of the spacecraft times its velocity, but all of this stuff that's coming off gives you a bonus. And so you actually get a little bit more than 1.0 of the incoming momentum transferred to the asteroid. That enhancement factor in the community is called beta, and beta is of great interest. And NASA actually has a mission called DART, which is aimed to be launched in 2020 to visit an asteroid and test kinetic impact on the asteroid. And I think I may have told a couple of you about this, but it's an ingenious idea. It's actually a binary asteroid. There's a big asteroid with a little moon going around it. 800-meter primary, 150-meter secondary. And the idea is to hit the secondary and change its period of rotation so that you can even measure it from ground-based telescopes by looking at the light curves and be able to measure how effectively it was deflected. Okay, so this is kinetic impact in a nutshell. What if that's not enough? What if the object's so big that that momentum injection is just not going to do the job? Well, you can use a standoff nuclear device as another way to do it. So basically, if you detonate a device just off of this, what's going to happen? You're in vacuum. Most of the energy of the device comes out as X-rays. Those X-rays are then deposited in a very thin layer of the surface, heating it and ablating it off, melting some of the material just underneath it. That material blows off of the surface. The momentum of all that material flying off is then equally imparted to the object going the other way, and it gives it a push. So that's nuclear deflection using a standoff device in a nutshell. And this was a calculation we did very early on as just an illustration of what's happening. This is energy density. That's why it doesn't really just keep going off. It's cooling. But really all the material is flying off. And then you're seeing stresses and damage inside the object. This thing was shattered pretty heavily the way it was modeled and the way it was driven. So that's nuclear deflection in a nutshell. Those are the two primary go-to methods of preventing an impact. A third one that is also considered for cases where you only need to make minor adjustments and you have a long period of time to do it is called the gravity tractor. It's basically using a spacecraft to tug the asteroid in a certain direction. But you can't just throw a rope onto an asteroid because they tend to spin and they're often not very cohesive. So you can't just put a big screw thing like you use for the dog and you screw the thing into the ground and put the dog on the rope. So, those ideas, you'll see them out there, but these things spin. Sometimes they tumble, they have strange shapes. So the idea is, as a rope, you use the gravity of the spacecraft and the asteroid use that attraction as the rope. And you only pull as hard as you can given how strong that gravitational attraction is. So it's very weak. Use your thrusters of some kind, and you sit there for years or even decades tugging, tugging, tugging in order to slowly build up a deflection. These two impulsive techniques, they get their change done right away, and so then it's just a matter of, simply speaking, it's close to being proportional to the time after that times an angular deflection or a temporal delay in the orbit. So in some cases, the deflection is insufficient, or it turns out that you have to push it so hard that it probably won't hold together. Now, you don't want to just barely break one of these up by pushing on it a little too hard, because you don't want to have 4 impacts of a quarter of the object in different areas. When you work through the scaling, it's actually worse than taking one hit from the bigger object. And so if you're going to disrupt it, and that's the only option, and you're going to take action, you'd want to do it very robustly. And we're talking about, you want to break it up into the smallest pieces possible, and you want to have the cloud spread as fast as possible, and there'll also be a net mean deflection that will come along for the ride with it. And we've done modeling where you can, if you intercepted, say a year and a half in advance, these clouds can be like of Earth-Moon distance and scale. And then the idea is, if something hits the Earth, statistically speaking, it's just sampling part of a much larger volume. You're not going to get hit by very much of the mass. And the asteroid provides natural protection up to about 10 meters, plus or minus 5. Or if you're willing to take the kind of damage from Chelyabinsk, almost 20 meters, the atmosphere is providing pretty good protection. And so this is a model of a little bit unusual asteroid. This was iron nickel, 50 meters, not your typical near-Earth object, but very tough. And basically a megaton class device in close proximity to this is just shredding this object. This is in the course of it coming apart. It continues to disassemble and break up into pieces, producing a large cloud of fragments. So that's sort of a last resort option. It has a lot of issues with it, but we're laying out options for potential consideration by the decision makers down the road. And if they say, gravity tractor doesn't work, we only have 5 years, it's too big for deflection, we're going to be pushing it so hard it might break up, what are our options? Well, if you get a lot of missions out there, you can try to do it in little bits. That would be a good option. Well, but what if we don't have time? What if we're not going to be able to muster enough missions? Well, if it's small enough, you might actually really be able to disperse it. So trying to put all this together, we created a plot where the vertical axis is log diameter. So it's proxy for mass and size, volume. And 1,000 meters is there up near the top. 2,000 is actually the top of the scale. 100 meters down here. And then time to impact. This is time if you're deflecting, either by kinetic or nuclear. It's the time from when you do that to when it would have hit the Earth. Okay? And what we see is this is 80 years. It's 20, 40, 60, 80 years. And what we show here is a region where, for a big, fast kinetic impact, or just one, but this is just for scoping purposes, 10 tons at 20 kilometers per second impact, it's a lot of momentum. I like to say it's 200 ton kilometers per second. That basically the boundary of the green is kind of what you can handle, and you see that, even with decades of time, you're limited to sort of 400 or 500 meter objects with a single impact like that. Above that, you're going to need nuclear push if you're only hitting it once. You can hit it multiple times, but Remember, this scales log, and the mass, which is what's important, goes like the cube. So sending 3 or 4 or 5 of these, it doesn't move you up very much. You can move up a little bit. And you need to send multiple missions to reduce mission risk anyway, that you may not succeed. But so if something develops that's large, really it's the only serious option. Now what we have down here on the left is my statement about how if you push it too hard, it might break up. And we found with simulations that even at 10% of the escape velocity of the object, imparting a velocity to it that's just 10% of what its own escape velocity is, you start risking having chunks come off. And then by the time you get down to the actual escape velocity, you're almost assuredly breaking these things up. Many of them have very low cohesion as it is. And they use the term rubble pile for many asteroids. It's just a bunch of material that's just loosely agglomerated. And so this region is risky, regardless of what impulsive technique you use. And this is the caution, careful, and that really hadn't been identified in the past until we came along and started modeling this and pointing this out. And so for my technical audience, we can switch to log-log coordinates. The major ticks are 1, 10, and this is 80 again. And so you can see that at about a decade, you have to either worry about whether one push is enough or whether you might be breaking it up. This is, if you're out more than a decade and they're not too big, kinetic impactors will do the job to get them there. But short time and big is a problem. If it's really big, a megaton won't do the job if you don't have enough time. So the orange-blue boundary is the region between where 1 megaton will work and where it won't. We shouldn't be too concerned with that, though, because we actually worked with a person from Sandia, Livermore, who's at Stanford working on his PhD, and he developed a rather sophisticated risk assessment model. And we cranked the numbers through, and it's a competition between consequences and probability. So the consequences are increasing with size, but the probability is dropping. And you'll see a lot of people making statements in the press saying, well, that's, the big ones are the problem. But we know that it depends, if you're multiplying two functions together, it depends on their functional behavior. Of which one's, is one going to 0 faster than the other one's going up? And so with his model, which is the best thing we had available, it tends to show that the risk is not from the largest ones, it's from the medium-sized ones. That the probability is dropping off pretty fast. And the other thing is the surveys are finding these things. They find the big ones first. And so they've almost found all the 1 kilometer and up ones. And then they'll work their way down successively. And the goal currently mandated by Congress was supposed to be met by 2020. They're not going to be able to do it because they weren't given the resources and the space-based telescope they'd probably need to do it, is to get down to 140 meters, find 90% of the objects 140 meters in diameter or larger. Well, that would bring us all the way down to here. Okay, that's a pretty good spot to be. But fortunately, it'd be nice to speed this up, but fortunately, these long impact intervals mean that we're not at great risk right now. But we need to work on it. And so this project and the efforts, I think, within the government and by the NNSA labs, it's kind of right-sized. Right? We're not sitting on the problem saying, oh, it's never going to happen. It's 100 years. It's 1,000 years from now. It might be tomorrow. We've gotten hit. Chelyabinsk, they didn't see it coming. Okay, or maybe it is going to be 300 or 400 years from now. And so we think it's appropriate to work on this at a certain level, increase our understanding, and be ready for the eventuality that, if you go long enough, eventually we will be hit again. So the research is really driven by two major sources of uncertainty. There's the accuracy of the models. We model something, how do we know the answer is right? Okay, you guys are familiar with this one. The other one we're also familiar with is we don't necessarily know what we're up against. We don't know what the composition is. We might know just that there's this bright spot of light, or dim spot of light actually, and somebody predicts that it's coming for us. We don't know exactly how big it is. The error on those light measurements is that you have to model the albedo of the object, how much light is reflected from it. That can vary by a factor of 5, 6, 10. There's huge uncertainty. And that just gives you effectively the area, and then actually what you're worried about is the volume, so there's an additional factor. So there's a big uncertainty on the mass of these things when they detect them. If it doesn't have a close pass, and you can do, in some cases, they can do radar observations using Arecibo or Goldstone. They can actually image these things. But you got to be lucky, it's got to come close enough. So some of the things that can affect the modeling of how these things are going to respond to the push, and in particular, are they going to break up? The size, the shape, the mass, the density, internal structure, the dynamics, they spin. So the most important thing is the orbit. You have to know whether it's going to hit. Do you need to take action? And so the surveys are of primary importance on this topic. Okay, all efforts should be made to find them before anything else if we had to make choices. And that's the way NASA's approached it, is they prioritize the surveys. And to nail the uncertainties, get the uncertainties down, because that drives the impact probabilities and when do we need to take action. In the FEMA exercises, and in fact in any real world event, after the fact, if there was an impact, and then you trace the chain of events backwards, you'll reach a point where the probability of impact was low. That's how it starts out. You get your first measurement, they watch this thing for a couple hours, they crank the numbers, and they say 5% chance. Well, that's pretty big on their list. Gets your attention. Is a world leader going to say, well, there's a 5% chance of this hitting, am I going to launch a space mission that's going to take 4 years and cost me $2 billion because there's a 5% chance it's going to hit me? 9 months later, they get told it's now 30%. What do? A year later, oh, we got a good measurement, it's 65%. What are they going to do? It's very interesting. It came out of, it's kind of unanticipated consequence, I feel, from the FEMA exercises. The evolution of the certainty of the impact will be a key issue should one occur. And who made the right call? Because if it's at 50%, half the time you're going to be wrong, and assuming all the modeling's correct and these numbers are correct, half of the time you're going to be wrong and half of the time you're going to be right if you launch a mission. You need to worry about mass. Here's a couple of California surfer dudes, and the one guy's reading a newspaper article after just having done that wave propagation calculation. So this is Suhail, I guess. Giant asteroid misses Earth, previously thought to be headed for Pacific Ocean. And the other guy saying, oh, bummer, dude. So it all depends on your perspective of what a good day and a bad day is. We call it validation. Other people call it a flood. So, like I said, mass is connected to albedo, and the uncertainty can be as large as an order of magnitude. But it's interconnected. It's hard to say, is it mass? Is it composition? Is it density, porosity? They're all interconnected. So for a particular composition, you have to say, well, what really is the porosity? And but we'd say this is the second most important issue. Third is composition, and so Here's an example for X-ray penetration. I talked about the thin layer, and basically at example X-ray energies of 1 kilovolt or 10 kilovolts, the penetration depths are microns to hundreds or 1,000 microns ballpark, but it varies a lot by composition. Deeper penetration gives you more kick because it's better to have more mass coming off at lower velocity than a little bit of mass coming off at higher velocity, right? And so an uncertainty in the composition of the object and how it will respond affects the efficacy of the push. And in particular, the presence of either high Z or low Z elements can play a big role. If you have ices, they may contribute to like a steam explosion, or they may, but it depends on how the water is locked up in the rock, or is it free water, or is it free carbon dioxide. Porosity. Porosity affects the effectiveness of kinetic impactors. The higher the porosity, the more it tends to dampen the shocks and the effect on the structure of the object. So porosity is good for preventing disruption. It lessens the damage to deeper into the object. And it influences the beta factor, the multiplier, on the momentum transfer. The thing is, as some of you know, porosity is complicated because we get into arguments when we're trying to discuss it about what porosity even is, because it goes from the very microscopic, almost atomistic scale to macroscopic, where you have two boulders and there's a gap in between them. So we're involved with tackling these problems, modeling porosity of all kinds, mesoscale, macroscale, boulders, smaller bulk densities that are really microscale porosity. Shape is important. This is a simulation by Megan of a kinetic impactor on an asteroid named Golevka. So this is one that wandered close enough to the Earth that the radar people got a snapshot of it as it rotated, and they built a shape model, and you can go online and you can download these shape models. And the point here is that if you hit a slope with a kinetic impactor, the resultant momentum vector is not necessarily aligned with the direction of approach. It tends to skew more toward the normal of the surface. And so the steeper the slope you happen to hit on, and it can just be the local slope, not the whole side of the asteroid. If you hit on a slope, you're not getting as much push in the direction that you were probably thinking or intending you were. And so we're studying the effect of local topography on the resultant momentum transfer to the object. And if the thing's rotating, then it can further complicate it. You might even know it was a shape, but now it's spinning, and your timing has to be exquisite if you know you're going to hit it at a certain point at a certain angle. It's hard enough to hit these things as it is. They're pretty small. And then, in addition to shape and porosity, there's other aspects of structure and interior structure that are important as to whether these things come apart or not. And interior structure, surface structure, does it have a binary? Like Didymos, the DART mission is going to the binary system. It's called Didymos. They sometimes call the moon Didymoon. And so, this is a model by Eric Herbold of the same overall mass, same diameter, but as an aggregate of discrete boulders, or as a more continuous material with included microporosity. And you can see the behaviors and the response between the two of them are quite different. And again, structure is multi-scale, heterogeneous, 3D. This is a computing nightmare. Very challenging, and it's pushing our capabilities to try to model these different kinds of systems. And then I mentioned spin. Spin can further complicate the response. It can enhance disruption. It can complicate shape effects. Predicting where you hit's tough. These are some simulations, again, by Megan of a kinetic impactor on a small object. And so when you lay them all out, there are all these characteristics, but in addition, there's also how could you measure these things? So we're in discussions with the community over how you can actually get a handle on these characteristics, and then what platforms can do those measurements. And so the modeling and the simulation are quantifying the implications of this, and we're also trying to use it to prioritize what to go after. And we're engaging with the people that are planning missions to say, well, this is important. This is not so important. And it turns out there's actually a lot of alignment with the science priorities. And so we're not too much at odds with what they're interested in porosity. They're interested in composition because they're working toward understanding the evolution and development of the solar system, and those are important for their goals as well. Okay, so asteroid impacts, as I said at the beginning, are a national security threat requiring advanced science and technology solutions. Deflection and disruption approaches might be used depending on the situation. Has difficult science problems, lack of knowledge of initial conditions combined. It makes it doubly hard. And as I may have insinuated, scenario-based approach is really needed because every case is unique and it's an integrated problem. And so some of our work with our NASA colleagues is to start looking at specific scenarios from end to end to be able to assess it in that manner and not just in pieces that really don't have much validity by themselves. And then to pick successive scenarios to try to start to populate scenario space and fill in understanding across the whole range. So thank you.